Dear students, today we start discussing the characterization of twice continuously differentiable functions, characterizing the convexity of such functions. This characterization using second derivatives is very important because this actually in practice allows us in many cases to decide whether a function is convex or not. So today we'll discuss this twice differentiable convex functions first, and then at the end I'll ask you a question from what we had discussed yesterday, so as to make you think how these ideas are linked with optimization. Now the first theorem is about a twice continuously differentiable function phi from R to R, simple real functions which you should be comfortable with. Then phi is convex if and only if the second derivative at every x in R is non-negative. Okay, that's what the theorem is. So it's a both way result. So if the function is convex, then the second derivative at every point is greater than or equal to 0. On the other hand, if the function is differentiable, twice differentiable, and its second derivative is greater than or equal to 0 at every point in x, then the function must be a convex function. So if phi is a twice continuously differentiable convex function, then we have already discussed above that phi double dash x is greater than or equal to 0. Because let me tell you, what has happened is that we have used the monotonicity property, and we can show from this whenever y is greater than x, phi dash y minus phi dash y is greater than phi dash x, which means that if a function is convex, the slope is increasing, that's the derivative is increasing for a single variable function, which means the second derivative at every point is greater than or equal to 0. So first part of the result is known. So what we have to do is to do the second part of the result to prove convexity of the function. How we will do this? How to proceed? Now I have information of second derivative, but I already know a complete characterization of convex function using the first derivative, which was this one. Which was this one. So now by knowing that the second derivative is greater than or equal to 0, can I reduce the whole thing in some way to this condition for convexity in first derivative? That would actually tell us that the function is convex. So let us see. Taylor's theorem, by the way, is a very important device which is repeatedly used in optimization. Optimization is a very clever way of approximating a function either by a linear function or quadratic function. The quadratic function is the name of the game, actually. In optimization, when you really go into computations, quadratic functions are really the name of the game. So here we start with the Taylor's expansion of our function around x. So I take any 2 point x, y say, and then around x I take a Taylor's expansion. So phi of y is phi of x plus phi dash x into y minus x plus half of phi double dash xi y minus x whole square, and xi lies in the open line segment joining x and y. Right? If x is bigger than y, then xi is bigger than x and smaller than y, and vice versa. Now what I know, I can take this part and transfer it to this side. But what I know is that this phi dash double xi is always greater than or equal to 0. See the power of the Taylor's theorem, just appreciate that. Just once you read the Taylor's theorem, the whole idea is clear, that once you know that phi double dash xi is greater than or equal to 0, then immediately you know that this whole thing is greater than or equal to 0. So what does it mean? It immediately told me that phi of y is greater than or equal to phi of x plus phi dash x y minus x, and this is possible for every x and y. So now by our previous result, we know that the function phi is convex. So how do we go to higher dimensional function? The trick again is to use this single variable ID and go to the higher dimensions. So how do we do that? So here we have to now be able to compute the second derivative of the function phi t, which is f of x plus th. You know that when for every t for a given x and h, phi t is convex. So we can actually prove that phi double dash t is actually this quadratic form written in terms of the Hessian at x plus th. Now I don't want to do a proof here. The proof is unnecessarily lengthy. Maybe when I want to convert this into some kind of books or something, I can have an appendix where this proof is being done. But I want to let you, or rather I want to ask you, the reader or the viewer, to really take your notebook and try this out for just a two-dimensional function when n is to R2. Function is from R2 to R. Once you do this, you can immediately take your, from n equal to 2 means you can write things for n equal to n. You can just take your, you make a jump in your vision, right? That's sometimes a good way of doing things. So now, putting t equal to 0, that is what we need. Phi double dash 0 is equal to this, h of grad fx square h. Now, which means here there's a mistake. It should be phi, this phi. So if phi is convex, because if f is convex, then phi is convex, which means phi double dash 0 is greater than equal to 0. Hence, we can conclude that f is twice continuously differentiable function, then for any x in Rn, this is true. And because h was chosen arbitrarily and x was chosen arbitrarily, this was true for any h either. So, which means that this is the property of semi-definiteness. So, whenever a function, twice continuously differentiable function is convex, at every point the Hessian matrix, when you calculate the Hessian matrix at any point, that is a positive semi-definite matrix. I would not like to go into detail much here. So, and we can go back also, right? We can go back. So it is so this is the result, that if f is twice continuously differentiable, then f is convex if and only if this is positive semi-definite. Now you can say that, okay, what about going back? If I know it is positive semi-definite at every point, is the function convex, the higher dimensional one? Here I would leave the whole thing to you. You use your definition, either you use your knowledge about expanding in Taylor's expansion in higher dimension, or you can use the definition of differentiability, twice differentiability of a function, and then can come to some conclusion. I leave this to you, because, and it's very important sometimes to take your pen and do things. That is the best way of learning some mathematical tools. There is no other way things can be brought to you, right? That you cannot say that, okay, I just listen, it's like a kind of YouTube, something is going on in YouTube, I see it's just like a movie or something and I'll learn about the subject. No, a subject doesn't come, like mathematics doesn't come to you in that way. You need to really engage with it. So this is the theorem. Again, let me tell you what the theorem is. So if f is twice continuously differentiable function on Rn, then f is convex if and only if at any x the Hessian matrix is positive semi-definite. So whatever results we have done for Rn, because Rn is just easy to handle, you don't have, there are not much technicalities. With little technicalities, you can do it for any open convex set. So, if U is, so however, whatever result that is holding true in Rn, then with an open convex set U, on which a convex function is differentiable, the same results will also hold true. You might not be able to use a real number thing, it will become little technically complicated. You may not be used to use a real function phi. I just did it from Rn to R because I was using the single variable characterization to get the multivariable characterization. So in order to impress upon the fact which I had shared yesterday, that convexity is possibly a unidimensional concept. So let us come to an example. So let us show that the following function, these are very important function for economists, x1 to the power alpha and x2 to the power 1 minus alpha. This function is of sometimes called Cobb-Douglas function, where x1 represents the capital input, this is a kind of production function, and L represents, and x2 represents the L, labor L. So with their respective weightage. So the production is nothing but a kind of a weighted product of the labor and the capital and the labor. So, and of course capital and labor has to be positive, otherwise you can't produce anything. Then this function, these x1 and x2 must be strictly greater than 0, and alpha has to be between 0 and 1. So you give an weightage to so how much you want to spend for how much you want to spend, make a capital expenditure, and how much you want to input in labor. So now I want to prove that this function is concave. F of x1, x2 is concave function. This is very important for economics. Instead, we will do a trick. We have not spoken much about concavity in the beginning. We will take the function which is the negative of this and show that it is convex. Once I can do that, I have proved that the function is concave. So this is the second derivative. I am computing the Hessian matrices. You will observe immediately that there is immediately a symmetry. It is twice continuously differentiable, of course. There is immediately a symmetry. You see that this mixed partial derivatives are equal. So once you do that, you compute the Hessian matrix. You put it here and compute the Hessian matrix. So those who know some bit of linear algebra would know that if I want to show that this 2 by 2 matrix is a positive definite matrix, I have to show that these diagonal elements are greater than or equal to 0. And the determinant of this matrix is also greater than or equal to 0. So these two are strictly greater than 0 is immediately apparent from this thing, and this total second order derivatives, these two are strictly greater than 0 is immediately apparent. So once that is greater than 0, then let us try to compute the determinant of this matrix. The determinant of the matrix you can easily compute it out by when you actually put in these values. You will immediately see that it turns out to be 0. And hence this matrix is positive semi-definite. This shows that G is a convex function on R2++, which means x1 and x2 is strictly greater than 0, and hence f is a concave function on R. So let us see how strict convexity, which is the important concept as you would have understood from the point of view of economists, how second derivatives are linked to it. If a function is second differentiable, how can we know whether it is just convex or it has some additional fact, that property of strict convexity? This result is a very important result, and that's what we are now going to discuss. So let us assume that you have a twice continuously differentiable function, and that this phi is from R to R. See, I am always trying to do it from the vantage point of R. So single variable functions, which is much easier to understand. And for economists, it is much more easier to understand because economists are much more comfortable with one variable function than multivariable functions. Economic students I'm talking about, but they have to get conversant with handling multivariable things. That is the key thing actually. Now, SB, sorry, it's not an S, SB are twice continuously differentiable functions. Please forgive me for little typos. I have to be slightly more careful. To prove this result, we again have to go back to second order Taylor's theorem. So you see the power of the Taylor's theorem that is coming in. So once you write it in the same way, you know that if this is strictly bigger than 0 and y is not equal to x, so take 2 points x and y which are different. So x and y are two distinct points. X is not equal to y. Once x is not equal to y, if x is equal to y, then of course there is nothing. If x is not equal to y, then it is strictly bigger than 0. Strictly bigger than 0. Now once you have this is strictly bigger than 0, then again use the same type of technique constructing the z lambda and all those things. You will immediately able to prove strict convexity. This will be x here, not y. Phi y minus phi x minus phi dash x, y minus x. Strictly greater than. So if you take any two distinct points y and x, y not equal to x, and you write this, knowing that this is strictly greater than 0, you will prove that this is also strictly greater than 0. And then use the same technique of the z lambda business, because here you have to maintain the strict inequality, strictly greater than 0. Because we have not spoken about the differentiable characterization of strict convex function, which is not so simple to get it immediately. So that is why we have not spoken about it. But once you know this, you can go back to strict convexity by constructing that z lambda. So what it says that, okay, if you have a strictly convex function, if you have a twice continuously differentiable function from R to R, and that is strictly greater than 0 at every point, then it is strictly convex. But the fact is that if a function is strictly convex, is this fact true? Is it a if and only if condition? The answer is no. For example, take the function phi x equal to xf4. This is strictly convex, but phi double dash 0 is 0. So we will now talk about higher dimensional strict convexity. So there we talk about something called positive definiteness of a symmetric matrix. A matrix A is called positive definite if the quadratic form xax, the inner product of x with the vector ax, A operated on x, is strictly bigger than 0 for all x element of Rn and x not equal to 0. This, in fact, one can show using basic optimization actually, but I will not get into this, or even basic linear algebra if you want to show. Say that this is true. Xax is greater than or equal to lambda mean A norm x square. If you know something about Rayleigh quotients, if you have learned something about Rayleigh quotients in your linear algebra class, then this will be immediately apparent to you. This must be clear to you. Please understand, if some people say that, oh, I do not know much of linear algebra, then one has to understand this is a PhD level course. So certain things are assumed, some basic linear algebra is assumed. Even if I put this in a book form, then also I'm hitting towards the graduate student in economics who is supposed to have taken some course in linear algebra. Positive semi-definiteness is, again we are repeating, which we have already said that our matrix is positive semi-definite. It is like this. It is greater than or equal to 0. So what does it mean? If a matrix is positive definite, then all the eigenvalues are positive. If it is positive semi-definite and not positive definite, and at the minimum eigenvalue, the last eigenvalue, at least has to be 0. That's the meaning. So let's go back. I will not prove it. Let's go back and let's write down what we can say about a strict convexity of a higher dimensional twice continuously differentiable function. So if we twice continuously differentiable function, you can ask why you are talking about twice continuous differentiability, not about just twice differentiability. Yes, these results would actually hold if you just write twice differentiability. You can prove that. But in optimization, we are always expecting our Hessian matrices to be symmetric, and twice continuous differentiability, if we assume that these second derivatives are all continuous, guarantee that symmetricity. And that is why, just to keep up the fact that what we really require more in practice, I am talking about these twice continuously differentiable functions. Mathematically, you can do a different, you can write different things. So if you have a twice continuously differentiable function, then it is positive definite And if the Hessian matrix is positive definite for all x, then f is a strictly convex function. But as I told you, reverse is not true. You can try out x4 plus y4. Let us look at two problems which you have to try out. So take a quadratic function with of this form, x qx, this inner product x with qx, and then inner product c with x plus d. If I say that Q be a n cross n symmetric positive definite matrix, then show that f is strictly convex. It's a very simple problem. You don't even have to use a pen possibly. Then it's a slightly harder problem to prove this theorem. Theorem 0.18 actually means this theorem. To prove this theorem above. And then can you write a similar result for concavity of the function? Strict concavity. How do you determine the strict concavity of a function? Okay. So with this, we will leave you with a question, two questions in fact. First question is there a class of strictly convex function for which the Hessian matrix is actually positive definite? That's one question we'll try to answer in the next class. And then another question which I will not answer is this. I'll just leave you to think. Just a moment, dear students. So once you know this result about convexity, this characterization of a differentiable convex function, can you tell us, or can you think what would be the nature of critical point of a convex function? If you have a differentiable convex function, and if you have a critical point, that is the point x star where grad of fx star is 0, then what would happen? Can you conclude something from here? So with this, I end this talk, and we will soon upload something about our first question.